Welcome to lecture 5 of AI Simplified series. In today's video, we are going to go over a very nice architecture for recurrent neural networks to solve one of the issues of recurrent neural network, which was very short memory time. So we're going to introduce LSTM, long short-term memory structure, where we resolve the issue. So without further ado, let's jump into the architecture and go over a numerical example together. All right, let's work on the architecture of LSTMs. When you roll out the RNNs and when you're using LSTMs in them, the cells are no longer a simple ReLU function that we had. It would be a more complicated connection of many inner components that we are using. To be honest with you, LSTMs, in my opinion, are unnecessarily complicated. I think there was a way to simplify it. Actually, it was simplified a little bit in GRU. We have a simplified version of these LSTMs, but they're amazing in addressing one of the problems that we mentioned about recurrent neural networks, and that was very limited short memory. So here we have long-term and short-term memory that we pass from state to state. And before, if you remember, in recurrent neural networks, we were only passing one state at a time, but in LSTMs, we are passing two states, one C states, the other one H states. The C state is for the long-term memory of your data, and H is mainly for the short-term part of it. So it's the best of two worlds. It is composed of many components. So here I intentionally use different colors because some of the nodes are having a sigmoid activation function, some of them tangent hyperbolic. So anytime you see a blue, that's a sigmoid activation function. And to remind you, sigmoid activation was an exponent of x plus 1 plus exponent of x. And whenever you see red here, like these two nodes, you have hyperbolic tangent. So tangent hyperbolic, for those of you who forgot what it was from high school, exponent of x minus exponent of negative x divided by exponent of x plus exponent of negative x. So let's get into it and see what it is. I think the best way to understand it is going through, again, a numerical example. And this time, I'm going to stick to the same example we had last time, which was using oil price to predict whether or not Fed is going to increase interest rates. If you haven't watched the recurrent neural network lecture, I highly recommend you go and watch it before watching this one. Otherwise, you may get confused a little bit. So anyhow, so let's break down what is inside it. So here, CT-1 is whatever state we brought from previous session. So when you start, there's no state previously, so it's usually 0, almost always 0. Same for H. So this is for long-term state, this is for short-term state. So the short-term state alongside your input goes through a fully connected network into 4 different nodes. These nodes that are colored by blue, like F, I, and O, which have sigmoid activation functions, are giving us a multiplier between 0 and 1. Sigmoid, to remind you, is a number between 0 and 1. It's like a faucet. So when it's close to 1, that means whatever input goes to anywhere, you make everything pass through it. Anytime this faucet is close to 0, you have almost closed the whole thing. You don't allow the stream to go forward. So these faucets, like FT, creates a number between 0 and 1 and goes to this multiplication with the previous state. So if this is like very small, let's say this is close to 0, 0 will be multiplied by this long-term memory, and what will go through here is almost 0, because 0 times anything is 0. This G that you see is the closest thing that we had before. So H in previous times, the nodes that we had in a ReLU function would probably be the closest thing you had here. So you had the input of X in it and the previous short-term state, and it goes through a hyperbolic tangent, goes to this gate, we call them input gate, and multiplies the value of that the I component creates. Again, this is a number between 0 and 1. If it's very close to 0, it's not going to update anything. It's not 0 because 0 times anything will be 0. If it's very close to 1, anything that is coming out of it will go directly here. And this additional information that came from mainly from X and your short-term memory will be added to whatever was left after the forget gate of long-term memory, and it will be your long-term state later. Okay, so this long-term state that is for later goes through a hyperbolic tangent, and then it multiplies by another thing, which is the output gate. So this is the output gate. Again, this is a number between 0 and 1. When it's very close, nothing out of, when it's very close to 0, nothing from it will go to the short state later. If it's very, very large, it's close to 1, everything that is going through it will pass through HT. So here, either HT will be your output, or this can be a function like logistic regression line on this to create, let's say, probabilities. In this example, we are assuming this is a logistic regression model. It has its own parameter too. So to remind you, the previous example, we had 3/4 of data on price of oil. Sorry, it was $70 per barrel, then 30, and then 100. And we wanted to predict whether or not this quarter that the price of barrels of oil is 100, the Fed is going to increase interest rates or not. So we want to predict this Y hat. I know whatever I said looks very confusing. This graph looks very confusing, but I promise you when we get into a numerical example, it makes way, way, way more sense. So without further ado, let's jump into it. So we start from $70. So let's go to the next slide. Okay, so here, as I said, we are having a fully connected network here. So X is all of the X is connected to F, G, I, and O, and H is also connected to F, G, I, and O. So here, H0, or initial state is 0. Initial state of long term is also 0. So the first step is actually very easy. I'm going to do the first 2 steps, and then I'm gonna give you the answer to you on the 3rd step, but I will ask you to do it by hand, because if you do it once, it will always stick with you. So in order to make life easier, I'm assuming the weights of H to F is 0.1, to G is 0.2, to I is 0.3, and to O is 0.4. So this is 0.4. By the way, if you have a piece of paper, please stop the video and draw the same thing, and please try to do it alongside me, because then it makes way, way more sense. And X is also fully connected to these. So the weight to F through X is 0.01, 0.02 for G, 0.03 for I, 0.04 to O. I intentionally use these numbers so that there will be low chance to screw things up. And here we have biases. I'm assuming the biases is always the same, and it's like -1 no matter what it is. So the bias of this is -1, bias of this is -1, and so on and so forth. I'm also assuming the bias for this logit function that we are going to use here, so let's say call it bias Y, is equal to -1. And I'm assuming the weight of that is come from hyperbolic tangent times I here is also 1 to make life easier. So let's start with the output of FT. So whenever I'm using blue, we are using logistic regression model. Logit function at the very first step. Okay, so F of 0 would be logit of 0 times 0.1 plus 70 times 0.1 times 70 plus its bias, which is -1. We said that all the biases are -1. So that will be logit of -0.3, and that will be 0.4255. So here you have 0.4255. Similarly, I think there is no need that I do it for everyone, because you can see that for G it's 70 times 0.02 plus 0 times 0.2 minus 1, which was the right. So that will be hyperbolic tangent of, maybe I do it just for this one, and then for the rest of it, I leave it to you. That will be 0 times 0.2 plus 0.02 times 70 plus negative 1. So that will be tangent hyperbolic of 0.4. So that will pass 0.379. Okay, so for I0, we're gonna have logit of 1.1, which will be 0.75. So let me write it here, 0.75. And lastly, we're gonna have logit of 1.8. I'm sure you can do it. It's just 0.04 times 70 minus 1 is 1.8. So logit of that, which is 0.05858. Fantastic. So we were able to tackle these. So in order to find the input gate, we just need to multiply. Okay, so maybe use another color. So in order to see the output of input gate, we just need to multiply these two numbers. So this value is 0.75 times 0.03799. Just multiply them, as you can see it in the graph. And that is going to give you 0.285. In order to get the value that is coming out of this multiplication, we need to multiply this by that. And 0 times any number is 0. So 0 is fed to this plus number here. 0.285 is also fed to this plus number. So our output for C, which is our long-term memory, let's call it C1 now, would simply be 0 plus this number. So that will be 0.285. So this is our long-term memory that is being carried forward. So now we need to find the hyperbolic tangent of that, because that also goes to this hyperbolic tangent. So tangent hyperbolic of 0.0285 is equal to 0.27758. So that's, and then we need to just multiply that by this number to get the short-term memory. So let's call it H1. So H1 is 0.27758 times 0.0858. It's not 0.085, sorry, my bad. It's 0.858 because we just found it here. Okay, so I had mistakenly put another 0. Okay, 858. So H1 would be equal to 0.2382. So that's the input to the next one. So here, this one was, C1 was the long-term memory that we carry to next step. This is the short-term memory we are carrying to the next step. And lastly, for Y hat, it's simply logit of 1 times this value, which was 0.2385, because that's what is fit there. And we said that the bias of that was -1. So that will give us 31.82%. So there is 31.82% chance that two quarters ago, based on the value of the price, value of the barrel of the price, the Fed would actually increase the interest rates. So now in the next step, when the price of the barrel of oil is gonna be $30, we no longer start from 0 because we already created these. So let's go to the next step. I'm gonna just write down the numbers. I ask you to try to replicate it and focus more on the values that were 0 before. Now they're not 0 anymore. So let's go to the next step. So in the next step, our H1 was 0.2382, and the long-term memory that we are carrying with us is 0.285, and the price of barrel of oil had become 30. So I only do it for FT so that you see what is going on here, and then I'm going to write down the rest of the answers. Let's not spend too much time on it, okay? So for FT, which is F1 in this case, F1 is simply logit of 0.2382 times 0.1 plus 30 times 0.01, and the bias is -1. Nothing is changing from the previous one. So if you do the math, you would get 0.337. So this is 0.337. So that means it tells you in this forget gate to forget almost 1/3 of this value. So what will be coming out of this gate, forget gate, will be 2.8 times this. So we're gonna slash 2/3 of the value. We will be only left with 1/3 of it. So the forget gate is gonna give us just 0.096, because 1/3 of point that is that. GT, based on my calculation, is negative 0.338. Since G is in red, it was hyperbolic tangent. That's why it got a negative number. It can get a negative number. Tangent, hyperbolic tangent is something between -1 and 1. The IT in this case is 0.492. So if you multiply these two numbers, the output of the input gate is telling us slash this by almost 50%. So what is going to give us is -0.1668. So now we need to add these two up. So 0.096. So what is happening is 0.096 plus this. These two numbers will be added up to create C2. So C2 would be 0.096 minus 0.1668, which is -0.0707. So that's the long-term memory we carry to the next round. So here we pass that through tangent, hyperbolic tangent, and the output of that would be -0.0706. And then the output of O, if you just plug in numbers, would be 0.7573. So you just multiply these two to get the output gate for HT. And if you do that, the multiplication of these two numbers is going to give you the next H, which is the short-term memory of you of negative. So H2 will become negative 0.04047. And then again, like before, we can find the y hat. So y hat 1 in this case, which is the probability that the Fed would have raised the interest rate in the previous session, is the logit of 1. I assumed that the coefficient was 1. Don't ask why you use 1. It could be any number. It's a tuning parameter. But here I assume it's 1. 1 times H2, which is negative 0.04047. And then the bias, as we said, was -1. So that will give us 26.1%. So now, since the price of barrel of oil has come down, the probability for the Fed to increase the interest rate decreased from 30-something% in the previous, I think it was 31.82% before. Now it's like 26.1%. So now for the next one, I'm just going to write down what the outputs would be, and I'm asking you to do it yourself. So y hat 2, so the C3, which is the long-term memory, it will shoot out. It will be 0.631, and H3 would be 0.532, and y hat 3 would be, y hat 2. So the prediction in this for this round would be 38.5%. Honestly, I think the best way for you to learn that is to created an Excel sheet and break down the whole thing. So put these weights in, put what would be the outputs and inputs of each one, and just pay attention that we have 3 gates. We have forget gate, we have input gate, and output gate. In each one of them, an output of a sigmoid function for forget gate is ft, which was a sigmoid function which guarantees it's something between 0 and 1, will be multiplied by the value that enters. So here by your long-term memory here. In this case, it, which is a sigmoid function value, would be multiplied by a gt output to make the input gate. So that is how much of the current contribution you want to pass forward to long-term memory, because it will be added to whatever is left from long-term memory here to create the long-term memory for the future. Here you create out of OT, you're creating again another value which dictates how much of the long-term memory would be carried forward to short-term. And lastly, that value would be fed into y hat to create the output. As I told you at the very beginning of the course, this lecture, LSTMs look extremely complicated for no reason. Honestly, I'm not sure why they're so complicated. I always had the intuition that they're more than necessary complicated. And we're going to see that in GRU, which is a significantly simpler structure, we almost get the same performance, meaning that we have both long-term and short-term memory, but in a significantly easier way. And we carry everything through one state. Instead of having 2 C and H here, we're going to only have H as a hidden state, but we make sure the long-term memory is also carried through it. So long story short, LSTMs are very powerful, very popular, computationally, relatively speaking, efficient, composed of a fully connected network that feeds H and X to 4 different functions. 3 of them are gates, F. 3 of them will be the multiplier of the gate, F, I, and O. They're all logit function. Only G is hyperbolic tangent, has nothing to do with the gate. So it's equivalent of assuming that in the ReLU functions, if you were replacing the recurrent neural network activation function of ReLU by hyperbolic tangent, you will only have G. So this was the core of what we had before. So this is the only place that we actually carry some information from the new observation forward, not as a gatekeeper. And these gates look like faucets. So the number F, I, and O generate dictates how much of the memory, short-term or long-term, would be carried forward. So in this case, like recurrent neural networks, it only suffices to find these weights. So I said these weights are 0.1, 0.01, 0.2, and so on and so forth. And the biases are -1, and I said the weight for y hat was 1 and -1 for bias. But where did I get these numbers? This is actually what should be trained during the training phase. And once you have that, you have already resolved the problem of very short memories here. So what I urge you is try to do this exercise on yourself. Draw the raw structure of this LSTM cell that I've created here and try to replicate those numbers. See if you can get those. If you do it once or twice, I think you won't be scared of this structure. Actually, it will kind of make sense when you do it. And all of my students have had the same experience. At the first time they were exposed to this, they say, oh, what the hell? What is that? But once they did it by hand, they say, okay, it's not that complicated. It's just a bunch of functions multiplied by each other, added up together, and give an output. But the intuition behind it is not too clear for me. Having like 3 gates, why not 2 gates? As you're going to see in GRU, a significantly easier framework resolves the issue and almost performs the same. But anyhow, thank you for staying with me, and thank you for finishing this lecture. See you in the next one.